Okay, so as students join in, you can go to joinpd.com and then you'll type in this code here to join the presentation. Okay, so as we wait for students to check in, you'll see a map of the United States, and you have two little icons in the upper right. You've got a flag and a little thumbs up emoji. And so I want you to drag the flag over the coolest place that you've ever visited. And I know it's not a very detailed map, so that might just be somewhere in Wisconsin. So you can put it as close as you can, and we can talk about that. And then I want you to put the thumbs up emoji over the number one place you'd like to visit. So a place that you want to visit, but you have not visited yet. So I'll give everybody a couple of minutes to drag their emojis over the coolest place they've been and the number one place they'd like to visit, and then we can share. All right, so we've got the flag down in Louisiana, New Orleans, or?
Yep.
When did you go down there?
When I was probably about 13.
Okay, what was the highlight of the trip?
I think just the culture in general. The food was amazing, and I mean the city itself is really, really cool. So
awesome. That would be one of my thumbs up for sure. It's on my list of places I'd love to go. And then you're going for DC for?
Yeah, I've never been there, and I really want to go there. So
awesome. Same here. All right. Oh, very cool. All right, as we get going, I'm just going to remind you about our online class expectations. So number one, I expect everyone to be prepared, which means being on time to our meetings, being in a quiet place, having any materials you need with you. So today that would be your chemistry note packet, and then not having any distractions around you. So if your phone is going to be an issue, just have that away. Any other devices, making sure you're not visiting other websites that are going to distract you. Secondly, I expect everyone to be respectful, which would mean, throughout the rest of the lecture, have your mic muted until it's time for you to share, and I can unmute your mic at that time. If you have questions are great. Questions are the root and heart of science. So I want you to have questions, and I don't want you to forget your questions. So best thing, if you have a question pop up as we are working, to just put that in the chat. And then if you wanted to ask a question rather than typing it into the chat, you can either just keep your hand up or click the little raise hand button too. That works just fine. And then I encourage everyone to have your video on. It does help just to make sure that I can see that you're paying attention and we can make eye contact, things like that. And then finally, I expect everyone to be engaged. So I want you to try your best throughout the class, make sure you're following directions closely, and then I want everyone to participate. If you're not comfortable participating orally, like in a back and forth discussion, when that is appropriate, again, you can always participate through the discussion board, through the chat. All right, today's little short class, I'm going to start out with a little balloon demonstration. We're going to review some of the unique properties of water that we've previously discussed, and then we're going to focus in on another of water and the water molecule's unique properties, which is its high specific heat capacity. So what the heck does that mean? That's kind of the goal for today, to figure that out. All right, so we're going to start out with a little balloon demonstration. Pretty simple little demo here. So I just have a regular latex balloon. And a guinea pig. Gotta have a guinea pig. This is my son Miles here.
Hello. Hi.
So, regular balloon filled with air from my lungs, and then I've just got a little tea candle here, which I'm gonna light with man's second best friend after dogs, fire. So a little source of fire, a little source of heat here. And so you can probably predict, as I move this balloon closer to the flame, to it's touching the flame, what's going to happen? Oh, it popped. And so presumably as the latex in the balloon started to heat from the flame, those molecules in the latex would have started vibrating faster, moving faster, until they started to flow and melt and create space for the air inside the balloon that was trapped under high pressure to quickly escape into the air in the room, which was at much lower pressure. And as that air moved from the high pressure in the balloon to the low pressure in the room, created that wind, which blew out my flame. Okay, so now this is where my guinea pig comes in.
Oh.
Okay, so now same balloon, only this time I put a little bit of water from my sink. So like a quarter of a cup of water. Basically, I put water in until it filled the balloon without stretching the balloon out. So now, just to make things interesting here, I'm gonna have Miles stand under the balloon. Okay, and I'm gonna do the very same thing. You're gonna look at it? I don't know if that's wise. All right, so I'm moving it down to the flame. It is touching the flame. It is on the flame. It is still on the flame. How you feeling, Miles?
That's good.
Not good? Okay. Still on the flame. Still on the flame. Now, check that out.
Oh, wow.
Okay. How you feeling now, Miles?
Oh, not good.
Okay, come
Not
back.
good,
Come
not
back
good,
here.
no.
Come back here. So, it's not popping. Oh, not trying. Oh, that's wax. Sorry, buddy. I'm gonna come back. It won't happen again. Sorry. Oh! So that, there I moved. Gotcha. All right. See ya. Thanks. There I moved the flame up to the side of the balloon so it would pop on Miles. But as you can see, I could have left that there for a long time, right on the flame. The latex is actually changing colors, it's blackening, and it's not popping. And so, that maybe shouldn't have done. Probably. Had to get them wet before I got them on here. So the question is then, why? Right? Why didn't the balloon burst with the water in it? So I want you to keep that question in the back of your mind as we talk about some of these properties of water going forward here. So before I tell you about this new property, this specific heat property of water, I want you to think back to our last lesson about some of the other unique properties of water that we discussed so far. And so take a second here. This is just a text, open-ended question, and tell me anything you can remember about something that's unique about water. When you compare it to other types of matter, other molecules, what's just weird about water? What's amazing about water? So take a minute here and write that down. I'm gonna keep cleaning up the mess I just made. All right, so let's take a look at the responses we got. It's wet. Oh, the debate. Is water wet? Well, if we're talking about, we talked about how it's a polar molecule, and so it sticks to itself, so it's always attracted to itself. So I would say, yeah, I would say it's wet. Okay, so let's go back and talk about the couple properties that we've looked at so far. Number one, super weird. When we talk about properties of matter, try to find a place to put my face. There we go. Water is less dense as a solid than it is as a liquid. So typically, as you move from a gas to a liquid to a solid, molecules get closer and closer together. They have less and less energy, and they're more and more dense. But water is weird. When water goes from a liquid where the molecules are flowing around each other to when it's solid, when it's in place and the molecules just vibrate in place, when those molecules arrange to form ice, they arrange in like a crystalline pattern, this geometric patterns. And by doing that, that creates this extra space. So there's actually more space between the molecules in ice than there is in liquid water, which means it's less dense, which means that ice floats. And so we talked about how that's important. You know, for number one, when our lakes in our area freeze over in the winter, the ice layer forms at the top. If ice was more dense, it would form from the bottom up, and our entire bodies of water would freeze over, which means everything in our lakes and ponds would die every winter. So that would be very bad. So that's one of the ones we talked about before. And the other properties we talked about is the stickiness of water. Because when we looked at the water molecule, when we looked at H2O, which is sort of this Mickey Mouse molecule, the hydrogens are held to the oxygens because they share their negative electrons. but they don't share evenly. Oxygen hogs those electrons and kind of holds it closer to itself. And so the oxygen side has a slight negative charge and the hydrogen side has a slight positive charge. And because of that, when water lines up, the oxygen side of one will stick to the hydrogen side of another. And so water sticks to itself, and that's what creates surface tension. And so on a basic level, that tension on the surface of the water allows for, certain bugs like water striders or even larger things like pileated lizards to scoot across and move across the surface of the water. And it also explains why belly flops hurt, because you're breaking through those hydrogen bonds that form that surface tension. But more importantly, right, this is why raindrops form. This is why water beads up. This is why everything doesn't sink in water, why stuff floats on the surface of water. If not for the surface tension, everything would sink down, even the tiniest particle. So it's very important. And not only did we talk about how water sticks to itself, but it also sticks to other charged surfaces. And so turns out most surfaces have a slight charge to them. So this is why water would, stick to the mirror or something when it condenses in your bathroom, let's say. But it also allows for trees and plants, because water is sticking to itself, but it's also sticking to the sides of those tubes that run through the stems of plants. And so it's almost, you can think of it like a string of beads. And so when water evaporates out of the leaves into the air and that water leaves, it kind of pulls the next molecule with it, and it sort of allows it to climb up, and we can have these massive, amazing trees that we have. All right, so that's kind of the review of what we've already talked about. Now we're going to add a little bit more notes to our note packet. So I want to give everybody a minute to make sure that they have their note packets ready. And so you can let me know that you are ready to move on and talk about this next property by just dragging that little blue circle icon to the thumbs up. I suppose if you can't find your note packet and we need to talk about that quick, you could drag that over to the thumbs down and I'll know you're not ready. So as soon as I see everybody is dragged over to the thumbs up, I will know it's time we can move on and talk about this next property. Go back to the balloon idea. All right, looks like everybody's got their notes on the whoop. Okay, so we're gonna move on. Whoop, went too fast. So back to why didn't the balloon pop when it had a little bit of water in the bottom? And this comes to the idea that water resists change in its temperature. So remember, you just need to fill in the blanks in your notes for the bold underlined words. And so the fancy science word for this, the term for this property is specific heat capacity. How much heat is it capable of absorbing and storing without changing temperature? And it sounds fancy, but we've all experienced this. We experience it regularly, especially in the summer. So you go to the beach and during the day, the sand is very hot. The sand and the water, they're getting the same sun, they're getting the same energy, but the sand gets really hot and the water stays cool. That's because the sand has a much lower heat capacity. A little bit of heat makes its temperature change quite a bit. Water absorbs that heat and changes temperature very quickly. It also holds heat really well. That's why at night, the water stays nice and warm. So when you go in and the air is kind of cool, beach is kind of cool, you go in the water, it feels nice and warm. So when we think about that balloon, going back to the balloon, that water at the bottom is in direct contact with the latex. So the heat from the flame transfers right into that water, and the water can just keep absorbing that energy without changing temperature very much at all. In fact, you could keep going there and until that water was boiling, the water will actually boil at a lower temperature than the melting point of the latex. So that's why it didn't burst. The water was absorbing that energy, absorbing that heat, and not changing temperature very quickly at all. All right, so why do you think this property of water would be important to living things? Why is it a big deal to life that water does not change temperature easily, that it resists change in its temperature? Well, the answers are still on there. I tried to have this deleted. So in any case, the hope is that this would be an open text question as well. So you could type in any thoughts you had about why it would be beneficial to living things for water to not change temperature. And then we were going to discuss these things on here and put them in the notes. So we'll just jump right to that part. So number one, we are mostly water. You know, depending on what type of organ you're talking about, or even how old you are, younger people have actually a higher percentage of water in their bodies. But no matter where you are in the body or how old you are, we are a majority water. And that water helps us keep a stable body temperature. We have to stay close to that 98.6. And if water didn't have this property, it'd be much more difficult to maintain a stable temperature where the chemistry in our bodies can function properly and our organs can all function properly. Secondly, we have lots of life. You know, a majority of life on this planet lives in the water, and most things can only live in a very narrow range of temperatures. So if it was swinging these big, huge temperature swings from morning to night and through the year, that would be very bad. And another big thing, another big impact this has on life is that it directly impacts climate. And so places that live near water, especially large bodies of water like the ocean, they're going to have much more stable climates, much more stable temperature. So if you consider like where we live in the middle of this great big land mass. And so we have very extreme seasons, very, very cold winters, very, very warm summers. But you think of a place that's very similar in latitude, similar position north-south on the planet, like say Seattle, Washington, they live right by the biggest body of water on the planet, the Pacific Ocean, but they have a much more narrow range of temperatures, much more milder winters and milder summers too. And it's because of water not changing temperature that it's like that. All right, well, that kind of wraps up our lesson for today. I appreciate everybody's participation and attention. You can always go back and look at this if I went too fast to fill in your notes. And we are going to talk about one more property of water next time we meet. All right. So thank you.